where an attacker has incentive to try to fool a machine learning algorithm, talk about the constraints in these scenarios, and talk about how one can in fact create effective attacks. So the first scenario we're going to look at is fooling face recognition. Right? So with face recognition, we use it to keep our phone safe. Right? I look at my phone in order to unlock it. Sometimes I look at my computer in order to unlock it. Face recognition is used at airports. Sometimes even for control of physical space in buildings, right? So it's easy to come up with a scenario where it is to an attacker's benefit to defeat face recognition, to say appear to be me so that they can get at the data on my phone. Now, the kind of constraint that the attacker typically works under in situations like this is that they don't actually have a hold of the system. Right? They don't provide digital input to the system that is doing face recognition. Instead, they maybe are able to change the environment that is captured by the camera to some extent, right? And that to some extent, because maybe they can't, if we're talking about an airport or public space, they can't necessarily change the wall behind the image that behind the person of whom the phone is going to take an image. But maybe if it's they who are mounting the attack, they can change something about the appearance of their face. So they can wear a hat or earrings or something like that. They also can't control the camera position or the lighting and so on. Now, here's where another type of constraint comes in, which is that beyond just how are they able to change pixels or can they change pixels of the input image, the changed input, if we're talking about changing physical reality, has to have the property, in most cases, that a bystander shouldn't notice that something strange is happening. Right? So if I try to walk through an airport wearing a paper bag over my head with somebody else's picture pasted on the front of this bag, I will probably fool any uses of machine learning-based face recognition. Right? But my attack will utterly fail because everybody will notice that there's a person with a paper bag on their head walking through the airport, and this will be undeniably suspicious. Right? So here, not only do we have constraints, not only does the attacker have constraints about how they can change the input in terms of can they control each pixel and by how much, but also the changed input has to have the property that somehow the changes have to be inconspicuous, not particularly noticeable to a passerby. So I'll talk about two attempts that we made to try to create attacks that in fact meet these constraints. So the first attempt started with standard attacks like PGD. When we added a bunch of additional steps to try to use these standard attacks as a method of attacking face recognition in practice. The first one was to restrict the modifications that are made to the image to the surface of eyeglasses. So if we had an image of Vicky McClure that we wanted to turn into an image of Terence Stamp, we would run, say, PGD on it. But in every iteration of PGD, we would throw away all the changes suggested by PGD, except the changes that were on the surface of the area of eyeglasses on Vicky McClure's face. Right. And you can run this algorithm and produce an image that will, in fact, most of the time, be successfully recognized as Terence Stamp. But this still doesn't take us close enough to having the image, this attack be realizable in practice. Right? Remember, we're not looking for attacks where we can hold up a picture to a camera. We're looking at attacks where the camera is facing the real world, taking an image of the real world, and I have to modify my own face in order to be misidentified as somebody else. So the next step is, several steps are all about enabling that. One is to smooth the transitions between pixels. Namely, we noticed that if you take a detailed look at a photo, right, then even in places in the photo where it seems like there are rapid transitions between light and dark, in fact, the transitions are very gradual, right? They're anti-aliased. So what we did next is we tried to make sure that the modifications that the attacker, made to the image also obeyed this property, that neighboring pixels were close together. And so this would have the change where before introducing this step on the Vicky McClure's glasses might have these rapid changes between light and dark. After we added this additional constraint, the changes would be gradual. The next step we added is to restrict the changes to the image to printable colors. Namely, if you're working in RGB space, as the computer knows about it digitally, you might produce lots of images that in fact, lots of colors that in fact, if you print them out, they don't come out faithfully printed on any printer. And if you take a picture of that with a video camera, again, there's some loss in translation, right? So we defined the so-called non-printability score, which is our own form of really color management, where we printed out a color palette as specified in RGB. We took an image of it. We compared the two. We assigned a penalty to all pairs, so all colors which we couldn't faithfully print out an image. And then we sought to minimize this non-printability score. And the last step that we added was to add robustness to pose. Namely, you see, as I'm giving this talk, I'm constantly moving slightly in front of the camera. Right? And if you asked me to be in front of the camera in a pixel perfect position that was identical to how I was in front of the camera 10 minutes ago, I just couldn't do that, right? I'm constantly in a slightly different position. And so I can't precisely control how any particular spot on my face is going to map to a pixel, or rather to which pixel in the image it's going to map. Right? And so in order to account for that, what we did was we performed the optimization over a set of images instead of just a single image of the attacker. So here, a set of images of then my student Mahmoud instead of a single image. And we were looking for eyeglasses that would successfully help with impersonation, not just for a single image, but when applied to any of these images. So, okay, so that's the sum of our first attempt. Let's see, what does the experiment look like in which we try to check whether this worked. Well, first, we needed to train a face recognition engine, which recognized some people who existed in physical reality who'd be willing to try to act as attackers. Then from among the people that the face recognition engine could recognize, we would pick at random one of the attackers, one of the people whom we had available in physical reality to be the attacker, and we would pick at random one of the remaining people to be the target of the attack. Then we would run the algorithm that I described to generate an image of eyeglasses. We would actually print out these eyeglasses on an Epson photo printer. We would cut them out or cut out the sort of the front plane of the eyeglasses and paste them onto a pair of eyeglasses that we 3D printed. And then the attacker would wear these eyeglasses. We would take video of them. We would extract frames from the video, and we would classify the collect images to see whether the impersonation was successful. The success metric here was the fraction of images that was misclassified as the target. To cut to the chase, in terms of actually fooling the face recognition engine, this worked pretty much 100% of the time, right? So Mahmoud, we could print out a pair of eyeglasses that Mahmoud could wear, and he would reliably be recognized in this particular experiment at Carson Daly. Right? So this showed that, yes, it is possible that even when an attacker is restricted so that they can't change every pixel exactly the way they want, they are limited to changes that can be implemented by wearing different types of eyeglasses. That is sufficient to fool a face recognition algorithm that might be deployed, say, to protect your phone or at an airport or something like that. What I didn't talk about is, well, what if the camera position changes more? Like, what if the picture is at an angle, or what if the lighting is very different? And I also didn't talk about how conspicuous or inconspicuous are these eyeglasses, right? So you might remember from the previous slide, those eyeglasses looked pretty noticeable. And in fact, this turned out to be something that we could not account for using the algorithm that is described, right? We tried to come up with various mathematical formulations of what it means for eyeglasses to be inconspicuous, to look like normal eyeglasses. And no matter how hard we tried, we just kept failing. Right? No way of constraining the algorithm made it produce eyeglasses that we thought were at all reasonable looking. So basically, we scrapped this approach entirely and tried another direction. So this is attempt number 2. The insight behind this attempt is that even if you can't mathematically formalize some of the constraints that you want an attack to meet, you might be able to capture them using a machine learning algorithm that you just teach what these constraints are by showing it a bunch of examples. What does this mean in this particular case? Well, here's our second attempt to generate more realistic looking adversarial eyeglasses. The first step is to collect a bunch of images, in our case using Google image search, of real eyeglasses from the internet. We chose only images of eyeglasses with a white background. We normalized the shape of the eyeglasses to this canonical shape that we were using. So basically we were only taking the patterns and colors of eyeglasses, not their actual shapes. So we use this data set now of normalized realistic eyeglasses to train a generator. So a neural network, which once it's trained, you initialize it, you give it some noise as input, a number between 0 and 1, and it outputs a realistic looking pair of eyeglasses because that's what it learned to do. In particular, we did this in GAN's style, so generative adversarial network style, where we paired the generator with the discriminator. The generator was being taught to generate realistic eyeglasses. The discriminator was taught to distinguish between eyeglasses that were real, namely that they came from our source data set, and those that were fake, namely that they were produced by the generator. And then we in the standard GAN style played these two neural networks against each other, penalized the generator for producing eyeglasses that the discriminator could tell were fake, and improved it in that way so its eyeglasses became more and more realistic. Now, so far, there's nothing adversarial going on. The only thing that's going on is we have a neural network that produces realistic looking eyeglasses. So the next thing we have to do is make these eyeglasses adversarial. And the way we do this is that we take this generator, we throw away the previous discriminator, and now we pair the generator with a face recognition neural network. Now, let's suppose this face recognition neural network, it can recognize a bunch of people, including me and Owen Wilson and Russell Crowe. And suppose that our goal is to produce eyeglasses that will help Owen Wilson be recognized as Russell Crowe. So the way we do this is now we play the generator and the face recognizer against each other. And in particular, we take eyeglasses that are produced by the generator, we digitally affix them to images of Owen Wilson, and we feed these images through the face recognizer. Right? And now we see, are these images at all starting to be at all, even a tiny little bit in the direction of being recognized as Russell Crowe, right? Do they move along the gradient from Owen Wilson to Russell Crowe? Right? And if they do, then we tweak the weights in the generator to make it more likely that to produce eyeglasses like this. If they don't, we tweak the weights in the generator the other way. Right? So we basically repeat this process, asking the generator iteratively to produce eyeglasses. So we see what effect the eyeglasses have, and then we adjust the weights in the generator to make it more likely to produce eyeglasses like that or not, depending on whether the eyeglasses were previously seemed helpful. And we run this either till convergence or until we exceed a threshold number of iterations. So I'll jump right to the result. In the end, we have a generator that is trained to produce eyeglasses that will help one specific person impersonate another person. And as before, we train a face recognition engine that we'll test against. We print out the eyeglasses and so on. Here's a short video of the results. Here's Mahmoud standing in front of, I think this is a VGG network, which very reliably recognizes him as Mahmoud. It also recognizes him as himself when he's wearing his own glasses, when he's not wearing them, or when he puts on these non-adversarial eyeglasses that are created by our generator. What you'll see next is he'll take off the non-adversarial eyeglasses, put on a pair of adversarial eyeglasses created by the adversarially trained generator, and now he starts being reasonably reliably recognized as a different student, Ariel. And for context, this is Ariel. So this is a substantial substantial gap being bridged by the eyeglasses between these two classes. Okay, so if you remember, I started on this attempt number 2 because we wanted an attack that was inconspicuous. There's a question of, well, how inconspicuous do these eyeglasses look? Now, inconspicuousness is something that's fundamentally in the eye of the beholder. So we ran a user study similarly to what Zico was talking about a few hours ago to check whether other people thought that adversarial eyeglasses were inconspicuous. I showed sets of eyeglasses to various people. Some of the eyeglasses were adversarial, some not. People were asked to tell us whether they thought the eyeglasses were real or fake. Now, here's a part of the result. On the y-axis is the fraction of time that for a pair of eyeglasses, people selected that the eyeglasses were real. right? So this is particular box and whiskers plot represents just real eyeglasses, and it's basically saying that for about 60% of real eyeglasses, for real eyeglasses, but 60% on average, about 60% of them, about 60% of the time, people thought they were real. So even for real eyeglasses, people often think that they are actually not real because they're aware that there's a possibility that they could be fake. If we look at the adversarial eyeglasses, they are less real looking, but one way of looking at this data is if we say, let's look at only those, let's look at how often is it that people label the average real eyeglasses? How often is it that? Sorry, let me step back. If we compare, one way to compare these two is to look the top 50% most realistic looking real eyeglasses and see how much overlap there is between that 50% and the adversarial eyeglasses in how often people said that they thought that these eyeglasses were real. And so one way of reading this data is to say that the most realistic 10% of physically realized eyeglasses, which is this little green tail that's circled in orange, they are more realistic than the average real eyeglasses. So at least in some cases, this kind of an attack can be made pretty realistic and pretty inconspicuous. Okay, so now through this, we've shown that we can create eyeglasses that not only one can wear in order to fool a machine learning algorithm, but also the eyeglasses can have the property that they're inconspicuous, namely a human won't think that these are particularly unrealistic eyeglasses. I didn't talk about controlling for camera position or lighting. I think for time, I'll skip that part. I'll also skip talking about defenses, other than just to say that if the attacker is aware of defenses, they can just train their algorithm to compensate for that. So all these things, all these things don't prevent the attacker from mounting successful attacks. I want to switch gears. So this was all about the attack scenario where we're trying to fool face recognition. I want to switch gears entirely, move to a very different scenario, one where what the attacker wants to do is fool a malware detector. In this situation, the constraints are also very different. The attacker digitally controls the input, right? They are the ones producing the malware. And so they can change every byte, every bit of the input that the machine learning algorithm is going to see. The constraint on this input now is just that the input still needs to be malicious. And if the attacker changed the input binary into something non-malicious, that wouldn't be helpful to them. So here's sort of the setup of this attack. We have an antivirus detector that's using deep learning in order to classify binaries as malicious or benign. The attacker has a binary, which unfortunately for the attacker is successfully classified as malware. And what they might want to do is they might want to transform this binary so that this binary is now classified as benign, right? Even though it's actually malicious. Right? But the constraints they want to change binary to have is that they want the binary to implement the same malicious functionality as before, and they might want the changes that they make to the binary to not be trivial to remove. Right? They don't want the changes to be removable by some sort of simple to implement filter that the defenders could use before passing the binary to the antivirus. So in this, to create an attack that will change malicious binaries into other malicious binaries that are not recognized as malicious by a malware detector, we use binary diversification techniques, which were originally proposed to mitigate return-oriented programming. So these consist of two different kinds of transformations. One is so-called in-place randomization transformation. So changes that change one instruction for another, or set of instructions for a different set of instructions, where those two sets or those two instructions happen to have exactly the same behavior. So this might be something like, if there's an add of a +1, you can probably replace it with a subtract of a -1, or you can reassign which registers are used as long as you don't cause any kind of register collisions. The other kind of transformation we use is displacement transformations. So these are ones where we allocate a new section at the end of the binary. We move some existing functional code to that section, add the appropriate jumps so that that code actually executes. And this just gives us more space in the binary that we can fill in with instructions of our choosing that might help fool the malware classifier. Now, how do we use these tools? Well, we take as input a malicious binary. The goal is to produce another malicious binary, but now that's one that's misclassified incorrectly by an antivirus as benign. For each function that binary, we pick a transformation. We apply this transformation to the function to create an iteration of a candidate malicious binary. If we check whether this new binary is in the direction of the gradient that's defined by the classifier, the antivirus program, if it is, then we keep that change and keep going. Otherwise, we throw away the change, and we just keep repeating this again until convergence or we hit a threshold. Now, we performed an experiment, one particular one that I'll tell you about, where we took 100 malicious binaries. We took 3 malware detectors that were sort of the state-of-the-art ones, and we measured how often we could change a malicious binary so that it was classified as benign. You see the results in this graph. So the most successful of our techniques is represented by the 3 bars on the right. Yeah, each bar represents attacks against a different antivirus classifier. The y-axis is the fraction of binaries that are misclassified as benign. So if the bar goes all the way, that means complete success. This left cluster of graphs is sort of a sanity check. What happens if you just randomly apply the functionality preserving transformations without guiding them using the gradient? Well, what happens is you get binaries that are still malicious, but still classified as malicious. They basically almost never successfully fool the antivirus engine. On the other hand, in our attacks, we were almost 100% of the time able to fool the malware classifier. Perhaps more interestingly, this success carried over to real antivirus malware detectors as implemented, as used by VirusTotal. And these were ones that we didn't even have access to. Sometimes they didn't even have, we didn't know whether they were using machine learning or how, but if for some particular tests, we could fool up to 50% of these real antiviruses by the transformed binaries. Okay, so this was a second scenario where I showed that in a real world setting, in a situation where an attacker has an incentive to fool a deep learning system, they might well be able to do it. Now, just to go back to what makes these attacks different from the kinds of attacks that there's been a lot of work on over the past few years. The property that I started out talking about is that the adversarial examples don't have to be close in LP space to their source inputs. So for example, for the eyeglasses, it's important that humans don't go and say, oh, look, there's a pair of really weird eyeglasses, there must be an attack going on, right? But beyond that, it's perfectly reasonable if these eyeglasses are even quite noticeable, in the sense that if I put on a pair of eyeglasses, you'll notice that the image without eyeglasses and the image with eyeglasses are pretty different from each other, right? But this kind of distance is actually not a problem for the attack in this particular case, right? So if we are going to apply any of the previous, any of the recent techniques for defending against attacks, well, maybe we need a totally different metric for what it means for 2 images to be distant, right? And not only is it not related to LP distance, but it has to somehow capture this weird concept of inconspicuousness. Are you going to be surprised if you now see a different version of me wearing eyeglasses or a hat or something else? With malware, again, the LP distance is irrelevant, right? The humans are not looking at the bits of the malware. It's perfectly okay from the attacker standpoint for the changed malware to be radically different in terms of bit per bit comparison or byte per byte comparison from the source malware, right? All the attacker cares about is that the functionality is preserved. The other important thing to notice is that in many attacks like this, the adversarial examples are very expensive to create. Right? It might take minutes or hours to train a network that's going to output eyeglasses, and similarly, some of the attacks on malware are quite expensive. So what this means is that for the various defenses that either require small LP distance or assume that the attack needs to be close in LP distance to the input that's being attacked, or that require many examples of attacks, well, those defenses don't scale really well to these kinds of much more practical and realistic problems. So I'll jump to the takeaways. So I showed with two examples that the real world applications of machine learning are vulnerable to the kinds of attacks that we usually see just in the image domain. I talked about how the methods for creating these attacks and defenses that we usually use, or the methods that we usually use for creating attacks on machine learning classifiers, and the defenses that we usually use, they typically rely on these the small LP distance constraint that doesn't imply, and so neither do the attack methods and defenses. And in general, it seems like defenses have a long way to go before they come close to being able to prevent attacks like these, which is consistent with what Zico was saying in his talk earlier in the workshop. And with that, I'd like to thank you for your attention. I'd like to thank my sponsors, and I'm happy to answer a few questions.
Thanks a lot for your great talk. So I will start with the first question. So basically for the face recognition, I see that from the demo, the person doesn't change a lot in terms of the poses. So would you like to briefly discuss how you could kind of extend your text so that it could be more resilient for photos taken from different views? Oh, you are muting yourself.
Yes, thanks for reminding me, and thanks for the question. Yeah, that's a really good question. Let me see if I can actually quickly go to that slide. So we were curious. I mean, we in these tests we asked the attacker to sort of not be 100% still, but we didn't ask him to turn too far from the camera. We did some tests where we did in fact tell the attacker, oh, now look left and right and up and down. And then what we did is we used an algorithm to measure the pose of the person. So we used an algorithm applied to the image to tell us how far the person was looking up or down or left or right, or whether they were tilting their head. And then we tried to examine what effect that had on the accuracy of face recognition, or the accuracy of fooling the face recognition engine. And we found out that approximately for how we had trained the attack algorithm, for each degree of looking left and right, the attack became 6% less successful. Right, so actually looking left and right had a pretty big difference. Surprisingly, we found that looking up and down, it helped some attacks and hurt other attacks depending on which network we were attacking. And that was really weird until we realized that some face recognizers were just really bad at dealing up and down, and they were worse at dealing up and down than our attack was. So the takeaway here was there's already some robustness, and the degree of the robustness depends greatly on the training data. Now, I think if we wanted really robustness to severe angles, then one of the things that we would have to do is build this into the process for training the machine learning algorithm that outputs the eyeglasses. And when I talked about how we do that, right, we talked about just pasting the image pasting the image of eyeglasses onto the image of a person. We would probably want to do some sort of affine transform to make sure that the eyeglasses are more as they see it would have been from an angle or something along those lines. Thanks for that question. So I see a question from Bo about right. Well, does the attack success rate vary against different models, especially for black box models? Yeah. So against in a white box setting, the attacks generally seem to be pretty similarly successful. In our experiments, they worked pretty reliably about 2/3 of the time. So basically, and what I mean by that is if you pick at random an attacker and a target, there was a 2/3 chance that the attack would be completely reliable, right? But then you would run across some combinations of attackers of targets where it wouldn't be so reliable. We tried how well an attack created against one algorithm worked against another algorithm. We didn't do any serious experiments. We just showed the input that worked against one algorithm to another algorithm, and that seemed to depend on the direction. I don't remember which way the direction was, but between OpenFace and VGG, it seemed like in one direction, attacks created against one network never worked against the other. But in the other direction, attacks created against one network worked about half the time against the other network. It would certainly be interesting to experiment with whether it would be possible to create eyeglasses that would transfer better to different networks.
Yeah, thanks for the answer. So another question is about like the malware detection. So I think I kind of understand that adversarial training to defend against these attacks will be pretty hard because it's very computationally expensive to generate attacks. But have you conducted a similar like user study to see for humans, if you look at these adversarial examples, could you tell them from like the common softwares?
Oh, if you're saying if a human were looking at a binary.
Yeah.
Yeah, so no, that's an interesting question. We hadn't. I guess the interesting humans in this case would be malware analysts, because malware analysts are probably the only humans other than the attackers who are likely to be looking at the malware. No, I think that's a really interesting question. I think one of the things that is on our to-do list is to talk to some malware analysts. We actually have some in the building where a lot of us work, but we just haven't gotten around to it yet. But yeah, it's a good question and suggestion. Thank you for it.
Yeah, sure. Yeah, thanks a lot for answering all these questions, and thanks a lot for your great talk.
Thanks very much for having me.
Mm-hmm.